All right, we are starting our last unit today. This is on solutions and colloids. We've already talked a little bit about solutions way back at the beginning of the year. We did some basic properties. We're going to review those. We're going to talk about how things dissolve. So if you're actually looking at molecules or atoms, how those things can break apart from each other and dissolve into a solution. Colloids are a very special kind of solution, and we'll spend a little bit of time with those. Not really today, though. They'll be probably next week. So let's start with a little bit of review. From the very beginning of the year, solutions were also known as homogeneous mixtures, which means that the mixture is the same all the way through. Solutions are also very stable, which means they don't spontaneously separate. These are not the things that you have to shake before you use them. When we did mixtures at the very beginning of the year, we talked about homogeneous mixtures and heterogeneous mixtures. And heterogeneous mixtures are the kind that you have to shake or stir. Things like salad dressing, or paint, or cream. Homogeneous mixtures are not those things. Homogeneous mixtures are the things that stay mixed. Things like maybe Kool-Aid, or pop, or juice. Those things don't usually need to be shaken before you use them because they stay mixed. Solutions are always made of two parts, or at least two parts. And we learned these words too way back at the beginning of the year. The solute is the one that you have in lesser amounts. The solute is the one that gets dissolved. So for example, like the Kool-Aid powder, if you were going to make Kool-Aid, the solvent is the one that you have in greater amounts, and it does the dissolving. If you're going to make Kool-Aid, the solvent would be water. And a lot of times the solvent is water. Water is called the universal solvent because it dissolves so many different things. Because water dissolves so many different things, and it's called the universal solvent, it has its own special category of solutions, and those are called aqueous solutions. Aqueous comes from the word for water, and it's just a solution where water is the solvent. We are mostly going to focus on aqueous solutions in class because those are the ones that we see the most often or that we use the most often. Why do things dissolve, specifically in water, but why do things dissolve at all? Why do things break down when you put them into a liquid? It has to do with the attraction between the molecules and the ions that you're working with, and we'll look at a couple pictures. Often this occurs where you have a polar solvent and an ionic solute. Those are words that we've heard before, but not for a while. What does it mean if something's polar?
Has a charge.
Magnets. It kind of like magnets, it kind of has a charge. Usually it has a partial charge. So part of the molecule might be positive and part of the molecule might be kind of negative. How about ionic? What's ionic mean? Strong positive and strong negative. Usually those come together and make a bond. What kind of elements make ionic bonds? What do you have to have? Yeah, you gotta have a positive and a negative. Metals and nonmetals typically. So when you have a polar solvent, like water, we learned that water was polar a couple months ago, and an ionic solute, something that has a metal and a nonmetal, you will get an attraction between the polar molecule and the ionic ions. These two kind of make sense. And that's why things dissolve. So what we have next is a couple of pictures of atoms and molecules. Yep, you are going to draw this. We're going to do an equation going across the top. And then we'll have the pictures underneath. I would like to dissolve sodium chloride. Is this the polar part or the ionic part? The ionic part. And yes, the S stands for solid. So we need that to know that we're putting a solid in first, and hopefully it'll dissolve in our solvent. Sodium chloride usually looks about like this. As a solid, it has its own crystal structure. Usually it's like a cubic kind of shape. Which atoms are the yellow ones? The sodium, because that's the positive, so the blue ones are the chlorines. And remember that ionic compounds are kind of like Legos. The formula that we write is the smallest ratio of parts. For every sodium, we have to have a chlorine. But when we make a salt crystal, we can just keep adding pieces until we run out of pieces. If we're going to dissolve that salt crystal, we have to take it and put it in water. So we have some water molecules. It's important to note which way they're pointing here. What part of the water molecule, the oxygen or the hydrogen, is the negative part? The oxygen. So on the oxygen end, there would be a partially negative charge. What part of the salt would that be attracted to? The positive part, the sodium part. So notice that I lined these water molecules up just like this on purpose, so that the negative oxygen would be next to the positive sodium. What do you think is going to happen to that sodium on the corner? It's going to dissolve. It's going to get broken away from the rest of the crystal because there's an attraction here. And that's what I was trying to show with this white line. There's an attraction between the negative oxygens and the positive sodium. So that sodium gets ripped away. And once it's separated from its crystal, then it just becomes the sodium ion. So Na+. And instead of being a solid, now the phase says AQ. What does AQ stand for? Aqueous. Aqueous, because it's been dissolved in water. If we drew a picture of that, we would have one sodium ion now, all by itself. We ripped it off the crystal. And as soon as it's away from that crystal, it can be surrounded by more water molecules. And again, notice how they're lined up. All the oxygens are pointed towards the sodium. That's on purpose because the oxygen is the negative part of the water and the sodium has a positive charge. Let's take this dissolving one more step. We still have our salt crystal, although this time it's missing a sodium on the corner because we already dissolved that part. What are we dissolving next?
Negative.
Probably the negative because we haven't done one of those yet. What part of the water would be attracted to a negative chlorine?
Hydrogen.
The hydrogen part, because the hydrogen part is the positive part. So this time I flipped the water molecules around. This time it's the hydrogens that will be doing the dissolving or cause the attraction that causes the dissolving. The positive hydrogen side is attracted to the negative chlorine. Just like before, that attraction causes the chlorine to be ripped away. Once that chlorine is all by itself, it becomes the chloride ion. And again, it will be surrounded with water molecules. And pay attention to which way they're lined up. This time the hydrogens are on the inside next to the chlorine.
So it's supposed to be an Na+.
Yep, because we still have the Na+. It's still floating around in solution somewhere.
Okay.
We just didn't draw it on this picture to try to keep it a little simpler. So remember that Na+ is still in there. It's still floating around. But now we also have a Cl-. Both of those are aqueous because they've been dissolved in water. This is the process of how things get dissolved. This process happens over and over and over. Every time you rip one piece of that solid away, more water molecules come in and they take another piece away. More water molecules come in and they take another piece away. And so piece by piece, whatever you're trying to dissolve gets broken down until eventually the whole thing has been dissolved. And a lot of times that means you can't see it anymore. This process has a name, and it's called solvation. Please note the spelling, not to be confused with salvation. Solvation is the process of something being dissolved. Some properties of solvation are that it occurs on the surface of the solid. Just like we saw in the picture, you have to pull the pieces away one by one. So the pieces that are around the outside of the solid are going to get dissolved first. The stuff that's in the middle or on the inside of the solid won't be dissolved until later. Solvation may be exothermic or endothermic. What does that mean? It might put energy out, or you might have to put energy in. We also talked about at the beginning of the year how those two words can be used to describe processes that make things feel either hot or cold. Same thing is true with dissolving or with solvation. Sometimes the process produces heat and it feels hot. Other times it takes heat in and it feels cold. The amount of heat that is caused by that change is called the heat of solution. And one of the things that we didn't quite get to this year that you'll do in Chemistry 2 next year is actually taking a measure of how much heat that is. How much heat gets produced when you dissolve some things, or how much heat gets taken in when you dissolve others. There are 3 factors that can affect how fast solvation will go. And if you just put a little bit of thought into these 3 things, they probably make a lot of sense. If you're trying to dissolve something in your kitchen, whether that's Kool-Aid powder, or maybe sugar, or salt, these are 3 things that you kind of just do naturally. First of all, you stir. If you want something to dissolve faster, you stir it. The reason that works is because you bring fresh solvent to the surface of the solute faster. Just like we saw in our pictures, the water molecules have to break away piece by piece of the solute. If you bring in fresh water molecules continuously, that process is going to happen faster. The second thing that you might do is increase the temperature, especially with sugar. A lot of people have experience with this at home. If you try to put sugar in iced tea, what happens to it? It usually just settles at the bottom. What happens if you put sugar in hot coffee? It dissolves really well. So if you increase the temperature, the solvent molecules, which would probably be the water, have more kinetic energy. That means they can move in around that solute faster and dissolve it faster. And the third thing has to do with surface area. Surface area describes how much area of the solute is exposed. If you have more surface area, it will dissolve faster because more of it's exposed to the solvent. You actually have more surface area with a powder than you do with a large chunk. And this is one of the things that we're going to look at with our lab that we're going to do tomorrow. No, we're not making tea.
Do we make Kool-Aid?
No, we're not making Kool-Aid either. Are we making anything? No, we're not making food tomorrow. A couple other things we need to know about solutions. One of the main rules of making a solution is this little phrase that likes dissolve likes. That means that if you want to dissolve something in something else, you want to mix 2 things together, they usually need to be similar in terms of bonding properties or in terms of intermolecular forces. For example, water and alcohol are both polar substances. They're both polar. They have a positive side and a negative side. That means they mix very well. When two liquids will mix, we call them miscible. Miscible means two substances are alike and will mix. This is how they make all of those adult beverages that they sell in the grocery store. If you look on the bottle, and you probably talked about this with driver's ed, right? The percent alcohol or the proof. That tells you how much actual alcohol is dissolved in how much water. The higher the proof, the higher the concentration of alcohol to water. If those two things weren't alike, they wouldn't mix. There wouldn't be an entire industry devoted to adult beverages. Two things that don't mix, you probably know this already, water and oil. Like salad dressings, you have to shake them before you use them. Water and oil don't mix, they are called immiscible. And they don't mix because they're different. Water is polar and oil is not. Water has a positive side and a negative side. Oil doesn't. So they won't mix. They will separate out into two different layers. We can use this idea of likes dissolves likes to give several examples of different kinds of solutions. So we're going to fill in a chart of examples, and your chart works like this. The first box will be the solute, and then you follow the arrow, and it's dissolved in a solvent. So that's how this chart works. The box on the left, before the arrow, is the solute. The box on the right, after the arrow, is the solvent. Most times when we think about solutions, we think about solids in liquids. That's the kind we have the most experience with. But you can make solutions out of any combination of the three phases of matter. So solids, liquids, and gases. And those would be the three corners of your triangle. What we're most used to is dissolving a solid in a liquid. So again, that's how this chart works. The solute is up here at the top. Follow the arrow, it's dissolved in the solvent. So solid in liquid. You could probably think of a lot of different examples of this. Ocean water is one. What's dissolved in ocean water? Salt, along with a lot of other things. Kool-Aid is another example that we've used quite a bit for solid and liquid. But what about going the other way? A liquid dissolved in a solid? That sounds kind of strange, doesn't it? It's not really dissolved, that's more absorbed. It's a little bit different, but interesting idea though. This one, you don't see as much anymore. But if you have, or if your parents have, fillings in their teeth that are silver, those fillings are usually made of something called Mercury Amalgam, which is a solution, it's a mixture of liquid mercury dissolved in silver. And it's such a tiny amount of mercury, it's trapped in the silver. It doesn't actually have that toxic effect on you that mercury vapors do, like when we talked about periodic table. So it's okay to use it in fillings, but it is a liquid dissolved in a solid. How about a liquid dissolved in a gas? If you think about summer weather here, maybe in August, versus heat in Arizona. Humidity.
Took you forever to figure it out.
Liquid dissolved in a gas. Water dissolved in air. That's humidity. So it makes it feel sticky outside. How about a gas dissolved in a liquid? A bet most of you drink one of these every day.
Oh, carbonated.
Pop.
Something that's carbonated, like pop. Carbon dioxide dissolved in a liquid, usually a sugar solution. How about gas dissolved in a solid?
A balloon.
This one's a candy.
What? Rock candy.
You're close.
Pop rocks.
Pop rocks.
Pop rocks.
Carbon dioxide dissolved in sugar. When you put that candy into your mouth, the saliva in your mouth dissolves the sugar that was holding the carbon dioxide, and the carbon dioxide comes out and it makes it feel like it's popping on your tongue.
Is that why it's bad swallowed?
Hmm?
Is that why it's bad swallowed?
They've done a lot of different studies on that. It really doesn't hurt you to swallow
Yeah,
it.
it doesn't do anything.
Yeah, if you ate enough of them, it probably would. How about a solid dissolved in a gas? Think camping.
Smoke.
Smoke.
Why do we have no?
Why can you see smoke? Because there's little bits of ash that are dissolved in the air around it, and it's actually the heat that carries it upwards. Okay, we're almost done. Not quite, because you can actually dissolve each phase in itself. You can dissolve a solid in a solid. What would be a mixture, a homogeneous mixture of two solids? Metal alloys are solid in solid solutions. Things like brass and bronze and steel, all of those are solid in solid solutions.
Water and alcohol.
How about a liquid in liquid? Yes. Any quote unquote alcohol that you purchase at the store is not pure alcohol. That includes things like rubbing alcohol. You could also put gasoline in that category. You could put antifreeze in that category. Last one. We're almost done. Gas in gas.
Helium.
Air. It's a really easy one. You don't think about it, but air is a mixture of a lot of different elements or compounds. That should be it for today. Homework tonight is an article to read, and then tomorrow we have a lab to do.